So we're continuing optimization, and what we need to make sure that we do is come up with our own equations, and okay, so pay close attention to example 3. We have 24 square inches of print. The way I'm reading that is if we have a rectangular piece of paper, I'm trying to make this look like a piece of paper, and the print is somewhere in the middle, and this is not, because I haven't actually read this, the top and bottom have 1.5 inches, 1.5, 1.5, and then the left and the right have 1 inches. And the way I'm reading this is the print is 24 square inches, so like this would be length and width, but I'm going to use X and Y because that's what I typically do. And now we are minimizing something. We want the least amount for the entire paper. So if I were to come up with an equation, I would start with X times Y, length times width has to equal 24. So then if I want to minimize the piece of paper, well, first I need to come up with an equation. Let's say I'll use P for paper, I guess. I'm just making up numbers. The paper would be, well, the X length, if I call this side X, well, all the way across, we have to add 1 plus 1, so X plus 2. And then if I call this Y, adding 1.5 and 1.5, we have Y plus 3. So we have too many unknowns if I wanted to do the derivative of that, but we can easily fix that by solving for one of these two variables. And I don't think it really matters what variable, you just solve for Y, so you get 24 over X. So the paper is equal to X plus 2 times 24 over X plus 3. And as I FOIL this, because I would rather do that than the product rule, which you could easily do the product rule. Well, X times 24 over X would cancel out the X's, and then we'd have plus 3X plus, let's see, it'd be 48 over X, but I'm going to write it 48X in the negative first, and then 2 times 3 will give me 6. So the derivative of that, P prime, well, that 24 is useless. Derivative of that would be 0. We'd have 3 minus 48x to the negative second power, and the derivative of 6 is pointless as well. So set that equal to 0, and I would go ahead and add over, which is how my brain works. And this is the same thing as 48 over x squared. So if you cross multiply, I'll go over here now. We'd have 3x squared is equal to 48. So divide the 3 over. Just making sure, because I always second guess my arithmetic. X squared would equal 16. And then the square root, you could have plus or minus 4. So x is going to equal 4. Well, if x equals 4, going back up here, that means that y must equal 6. And it is worthwhile to mention, and I haven't done this yet, to mention why it's a minimum. Well, if you were to go back to this derivative and make your sign analysis, and I like how the author doesn't even look at negative values, because these word problems, the context of having a negative doesn't make any sense. So if you were to plug in, let's say, 2 into this problem, well, 2 squared would be 4, and it'd be 48 divided by 4, which is 16, and 3 minus 16, we're going to get a negative. And then if I were to do this to the right, so if we have a negative derivative, that means that we go from decreasing, going down, to increasing to the right. So that does confirm that x equals 0 was a minimum. And we need to make sure that we answer the questions. What should the dimensions of the page be? Not x and y, So going back to this part, if x is 4, 4 plus 2 is 6 inches, and y was 6. So 6 plus 3 would be 9 inches. Yeah, I think that is good. You can see how difficult these problems get. And just for the sake of showing you a little bit different work, his work is definitely different than mine. Well, maybe it's pretty much the same. No, he had x be the other variable. X was up and down. I knew something was off about that. But you get the same answer. So it's very possible to have different work, same answer. And every teacher teaches it slightly different. So you might go to college and get a completely different explanation on these. Just showing you what works for me. Here's another problem. We want to find the maximum area for a rectangle. Again, I'm going to use x and y. That's just how my brain works. So a rectangle is bounded by the x-axis and y-axis. So this picture says 1,000 words. And we have this equation, y equals 3 minus 1/2 x. I think I would just come up with an area equation, which equals x times y. And based off of this problem, y is equal to 3 minus... So replace y with 3 minus 1/2 x. And then I would FOIL, or it's not foiling, I'm sorry, it's distributing 3x minus 1/2 x squared. So if we did the derivative, it'd be 3, bring the 2 in front, it'd be 1, x would be equal to 0. So x would equal 3. If you did a quick sign analysis, I guess I'll actually do it the correct way, where you put 3 down and like 3 on this side. But remember, it's 3 minus x. So as a 0 to the left, if we had picked it like 2, we would get a positive value. 3 minus 2 is a positive number, and to the right is a negative. So we're going from an increasing to a decreasing. So it is a maximum. Increasing hits 3 and then decreases, so it is a maximum. And so that's the length, and you can plug in, so x is 3, so that means y would equal 3 minus 1/2 times 3, 1/2 times 3, which, pretty straightforward there, would be 3/2 or 1.5. And yeah, what length and width should the rectangle have to maximize its area? A little bit trickier of a problem, but very doable. Determine the point on the line y equals 2x plus 3, that the distance between the line and this point is a minimum. So we're minimizing. That's your clue that it is an optimization problem. Now, what equation should we use? Well, a little bit trickier here. Well, it's a distance problem. So the equation I'm going to use is the distance formula, where, in case you haven't done this in a while, y2 minus y1 squared. Usually people start with the x's. I'm not sure why I start with the y's. And we don't know what point on this line hits it, but we do know that this is always one point. So the distance equation that we could use is definitely going to use 2 for y. And I'm going to use this y as this expression, that 2x plus 3 squared. And then this x coordinate is always 1, and it corresponds to the x that's always in that problem. Let's clean that up a little bit before we try the derivative. And maybe I'll rewrite that derivative as to the 1/2 power. The square root as the 1/2 power. And, oh, that's kind of ugly. That's not too bad. Let's do 2 minus 3 first. So that would be -1 So we have negative 2x minus 1. That'll help me because negative 2x times negative 2x would be 4x squared. Let's see, it would be a positive 2x plus 4x, and negative 1 times negative 1 is positive 1. And same thing with that. We're going to have a plus, let's see, 1, let's see, minus 2x, and then plus x squared. Ugh, kind of want to clean that up too. This is kind of like a habit of mine, I guess. Alright, now let's do the derivative. So bring that 1/2 in front. It's now to the negative 1/2 power. I'm already not liking this problem. And then the derivative of the inside would be 10x plus 2. So maybe I should clean that up a little bit. This is the same thing as, let's factor out a 2 from that 10x plus 2. So we're looking at 5x plus 1. And in the denominator we have 2, and then the square root of all that stuff. Well, at least we can easily identify where the numerator equals 0. That would be negative 1/5. And my gut is telling me that this is not factorable. I don't think it is. Yeah, because you do want to see where the denominator also equals 0, because remember, the minimum can occur where the derivative does not exist. The issue that we have is if I do the quadratic formula here, like, because you can square both sides, so we really don't care about the square root. X equals negative b plus or minus the square root of b squared, which would be 4 minus 4 times 5 times 2, so that would be minus 40. Yeah, we're going to get a non-real answer in the denominator. Over 10. I mean, it's pointless to keep going on because the denominator can never equal 0 in this problem. It could in the future, though. Let's see. So that's the x-coordinate on this line. Let me change colors one more time. That's the x-coordinate on this line. It's like right here. And so what you also have to do, because it does ask for the point, we want to plug in negative 1/5 in for x. So that would be negative 2/5 plus 3. Let me write that out. Negative 2/5. Let's write that as 15/5 is the same thing as 3. So the ordered pair we're talking about would be negative 1/5, the x-coordinate, and then that adds to be 13/5. Whew. These are doozy of a problems. I think I'm going to stop right there. I think I have more in the notes, though. So hit pause if you need help with any of this. Oh, I guess I am ready for the homework. I do recognize that there are more example problems, but maybe what we'll do is we'll save those for our Google Meet. So try them on your own, because I don't have an answer key for them, and we can discuss those when we get to them.